All right, thanks everybody for coming to the AI seminar. It's my pleasure to introduce Sean Taylor. So Sean Taylor is a co-founder and chief scientist at Motif Analytics. Before that, he was a data scientist and head of Lyft's rideshare labs and spent 7 years as a research scientist on Facebook's core data science team. Sean's work is at the intersection of experimentation and causal inference, with a focus on applied problems and generating business value using the latest methods. He earned his PhD in information systems from NYU's Stern School of Business, as well as a BS in economics from Wharton. Sean, it's all yours.
Thank you very much. It's so weird to hear your bio that you wrote read to you. But yeah, thanks for the invite. It's really nice to be here. I obviously left my academic life behind a while ago, but it's just like really valuable to me to come back and stay in touch with the academic world. And even my first slide is kind of about this, just to talk about, to frame this problem, because what I'm going to talk about today are very applied problems that I've encountered in my job in industry. And like, why am I talking to you today about it? And I think it's because I get a lot of value out of this matching exercise that I try to do a lot, which is like stay in touch with my academic friends, what they're working on, what kinds of problems that they're interested in, and then try to find opportunities to match, you know, the work that they're doing to the stuff that I'm doing in industry, and sort of like be this matchmaker. And a lot of value is created this way. And I think coming to talk to you about this problem that I'm working on is kind of maybe my opportunity to seed the idea that it's interesting and that maybe you want to tell me how to solve it. Because I don't have all the answers, and I kind of want to just give you my thought process about how I've been working on this problem that I've been working on, and try to stimulate some discussion about it. All right. So I want to talk about opportunities, and I think that there's this sense that when we work with data in companies, that we're producing value in some circuitous way. Like we don't really know the actual process by which the value is being created, but we do it, and there are examples of it, but it's hard to exactly define where the value is coming from. And in analytics in particular, there's just sort of these teams of people whose job it is to answer questions for people who work on products and produce what they sometimes call actionable insights. Like it's like something that you learn from the data that causes you to maybe take a different course of action. And to me, as a causal inference person, this has a real causal flavor to it, right? There's this sort of like a proposed intervention of some kind is being generated by working with the data. And I spent a lot of my career working with A/B tests, where often the hypothesis or the insight already had been had a while ago before we got to the A/B test. The A/B test is the sort of like culmination of the insight turning into a product change, and then something that we're testing and measuring and evaluating. But the thing that happened before that has become kind of interesting to me, and that's what I've started to work on in the last year and a half or so. So just going to give an example of this to ground it, because I think like from a product analytics world, which is the world that I'm in now, there's just this way of talking and thinking about things that I think I just want to make sure we're grounded in an example. So this is like a screenshot from Amplitude, which is the product analytics tools website. And what they're doing is trying to sell their product, right? And they're trying to sell the act of using their product as being useful to a company. And so what they're saying is that this is an app called Calm, and the people analyzing the data on the Calm app realized that very few users were finding and using this reminder feature. And they found this association between usage of this reminder feature and retention in the product. So a 3x increase in retention for people who set daily reminders. So they like discovered some association. And then they ran this experiment where they kind of nudged people to use this feature more often. And then the result was that retention went up by 3x. Magically, it was the same as the correlation that they found before the experiment. So I sit down, and when I see stuff like this, I tend to draw DAGs. And so, okay, there's this association that they found between scheduling daily reminders and the future product usage. And that DAG is like kind of, it's a proposed DAG. But there's this threat to validity here, which is that there's just this interest in meditation, and people who are more interested in meditation will set reminders, and they're also more likely to use the app in the future. And then the experiment is essentially an instrument that they apply that produces an exogenous shock to scheduling daily reminders and produces an identification strategy for the measurement of this association that they have created. And then, you know, in this example, they found that there is no confounding, which is, I think, somewhat implausible. But, you know, like to them, it was like verification that, finding this original association was the valuable part. The experiment was just sort of like bookkeeping about how valuable is it, but in verifying that it is. But the interesting part was when they were just analyzing the data and just looking for associations. So as a causal inference person, this is sort of like a little bit perturbing, because it's not like what they did that was valuable wasn't like rigorous causal inference. It was informal causal inference. They just found an association, but it was a strong association, and it was pertaining to a variable that they really care about. And I think this is something that we all do in the real world a lot, is we do this kind of casual causal inference, and it's very valuable to us, and we don't have to run experiments because the associations are so strong that they're almost sometimes self-evident. And when they're not, we can follow up and do the work that we need to understand, if they're really causal. So this activity of find just this part of the DAG, the hypothesis, is actually really interesting, and I think a little bit under theorized, and we don't have a lot of tools, or at least I don't know of a lot of tools for where do hypotheses come from in the first place, I guess, is like kind of the start of this work. And I think, like, if you think about where do hypotheses come from, you have to go back to the act of observation of a system in some ways, like, which is as humans, we're recalling things that we see and hear, and our sensory and perceptual systems are the reason that we're able to come up with hypotheses about causal relationships. At a company, we never directly observe people using our product. You can, but it's in a very limited way. What we have to rely on are instrumentation that we create that creates these event sequences. And so the kind of primitive data format that almost every person who works at a company deals with are a set of kind of actor, timestamp, and event triples, is one way to think about it. So this is very, very like primitive data format. It's very flexible. It accommodates a lot of different problems. And as someone with econometrics training, it's sort of like looks like panel data to me. It sort of has this flavor of, oh, we have repeated observations of the same unit of observation over time. And in fact, like most standard analytical approaches that you'll see will tend to do some kind of aggregation before doing analysis on data like this. And I think that makes a lot of sense. We have really good tools for working with matrices in general. And so it's sort of like really convenient to convert this into a matrix and treat it that way, but it does destroy some information in the process. And I think in a lot of ways, some of my hypothesis in starting to work on this project is that initial destruction of information that we're doing is like preventing us from seeing and learning about hypotheses that we could generate otherwise. So it's sort of like we compress the data too early, and maybe if we delayed compressing it until later, we would learn something different and maybe more valuable. Any questions about the setup? I just want to pause here. Okay. I think that and part of the kind of like additional motivation for this is that there's just sort of like, in general, the success of data-specific approaches to answering questions. If you know the structure of the data, you can use different sets of tools. And this is just a well-known thing. And I think if we work with spatial data, we know it's going to end up on a map. And so we can leverage those properties of the data in a certain way. If we work with image data, we know something about it. But in event sequence data, I found that there's really not a lot to go on here. I think there's a relationship to strings and text that you could use, and I'll talk a little bit about that. But I think in general, I found that working with event sequence data is very challenging because it's high dimensional, it's irregular. And so like we had to kind of start thinking about different tools for working with it. And so just if you think about the perceptual system you're trying to create for someone, is that in the data that supplies it, it needs to be mapped into a low dimensional space that they can visualize and interact with. And so like we need a set of tools to work with event sequences and to project them into something that people can interpret and that like reveals these insights. Okay, so we have the data set aside. What are we doing with it? Well, I talked about this like kind of causal hypothesis generation, which is the goal here. I think you can break it down a little bit further into this 2x2 diagram. So at the very bottom left corner, we have this idea of like, I know the potential cause and I know the effects, and I'm just testing it. I'm just measuring some strength of the causal relationship between two concepts that I've already measured, I've already operationalized. But there's the other quadrants where you don't know what the consequences of actions are, or you don't know what the cause of an effect that you observe is. And I think that a lot of people who work in businesses spend a lot of time in quadrants 2, 3, and 4, and only when you finally like have operationalized these concepts and decided on a hypothesis do you move into quadrant 1. And so really what I've spent a lot of time thinking about is in the last year and a half is just how do we do tasks 2, 3, and 4? Is there a way to formalize them a little bit better? and sort of like make a known or unknown cause known, or at least like known better than just like a totally unknown thing. So this is very much in line with exploratory data analysis and hypothesis generation, but just sort of like specifically applied to the idea of looking for interventions that might be productive for some particular use case. So the research questions I've been working on to formalize them a little bit more are, how can we generate hypotheses about causal relationships in systems that we can't directly observe? So we do this naturally as humans in systems that we can observe. How do we port that into a system that we can't really directly observe? Our perceptual system is really determined by the data that we're collecting. And then how can we combine a modeling, visualization, interactivity approach to enable human analysts to do this, which is kind of building the perceptual system. You think about your eyes as a type of perceptual system. They do transmit information into your brain. They also have interactivity built into them. They move around and scan the environment and change where they're looking. Okay, so we have this data set. It looks like events. What are we going to do with it to understand it better? Well, we have to model it, right? It's already high dimensional. We have to apply some idea of a model in order to project it into a lower dimensional space for us to understand it. We can think about an observed event sequence. We can think about a type of conditioning that you do on sequences, which is, there's different kinds of conditioning you could think about, but a very simple form is to say, like, I know something up to a certain point, and I have to form what is effectively a forecast of the future events that I will observe in this system. And I'm going to introduce another concept, which I think is like, I haven't quite like figured out a formalization of this that I love yet, but like there's this idea of an interventional distribution here, which is like that I could make an event be the next event in the sequence. And this is like related to normal causality, and I think you could take like other cross-sectional causality methods and frame them this way. But I do think it's sort of like a little difficult to think about what that exactly means in some cases. Now, like if the event sequence has an event where a user is assigned to a random to an experiment and it's randomized, then this is a very easy to think about distribution. It's like the user was assigned to A at this time in the event sequence, or assigned to B at this time in the event sequence. This interventional distribution, very well defined, easy to estimate, and the challenge becomes statistical in nature. But what if we just treated every event as an intervention and just for now reserved our like judgment about whether that is a causal relationship or not, and see how far that goes, and then we'll work backward to say like, what does that really mean, and is it what we think it means? Okay, so to convert this into something that we can work with as practitioners of causal inference, we have to take the sequence and apply some dimensionality reduction to turn it into three variables. Very, very similar to reinforcement learning setup, where you sort of have like a state, action, reward setup. So at every point in the sequence, you can think of like what we know up until that point as the context. Then the event itself is like, we could think of it as something that we can control, even though we don't always have control over it, and that's the action. And then what happens as a result of that into the future is the outcome. And this naturally kind of creates like two main estimands of interest, which are the conditional distribution. So what happens in the future if I change this event conditional on the rest of the past? That's this conditional expectation. And then there's just this kind of like probability distribution over context. So how common is this context? Is this something that comes up very often? And if we have these two tools, we can do a lot of things to help users solve this problem of trying to look for interestingness. I just want to point out that conditional distribution and the probability distribution are sort of like overall prefixes. So it's a very general object that captures like probability of like all substrings that start with the start of the string. And so that's sort of like handy because you only need one object to apply to the whole sequence. Okay, so let's break it down to these. Let's say we compress the sequence into three steps. There's the context, there's the action, and there's the result. And we could just sort of like assign, if the string is length 3 like this, then we can like map it to this tree structure, and then we could assign transition probabilities. And so now we have like a complete model of that system. And so now, like, if you think about the analyst problem, I would like to know how common is this context? So how often does it come up that this event could come next or not? Then what is the causal, I'm going to like use scare quotes, the causal effect of the difference in the outcome given the action? And then these are two statistical problems, right? So we'll talk a little bit about how to estimate these quantities and what we've been doing to do that. But then there's the interpretation side of things, which is, can I, this is in the domain, this isn't domain knowledge, right? The data won't tell you this, but can I enact a change in that distribution? Is it interventional? Is it an event that I can cause to happen or not? Which is like, I think, often not like a binary thing. I think it's like something that people can think of ways to make events happen more often or not. And so we have to think of it as like an act of human creativity to like, is it possible to change that distribution? And then is the effect causal? So that difference in magnitude, is it so confounded that that the difference between those two things like wouldn't persist if I did create that intervention? So it's kind of an interesting way to like relax the constraint of causal inference here, which is like that, like how interventional is the distribution? What's the cost of moving this P of D given X into a new state, into a different probability distribution? And you think about like in an experiment, the cost is like free. Like I can set that parameter of whether that event will happen next. But in other contexts, it could be more costly. Like I'd have to design something. So sort of like bringing the practicality of how hard it is to create an instrument into the mix. Any questions about the setup so far? I just want to note that the reason I'm doing it this way is that we just don't have experiments usually in the data. So we're doing the analytics data that we have has some experiments in it, but usually doesn't. And so we're sort of like resorting to just looking for strong associations and trying to figure out and then letting a human analyst decide, like, is that an association that I think I could turn into something? So there's still an important role of domain knowledge here. But in a lot of causal modeling, the domain knowledge comes first. It's like you specify the model with domain knowledge. I think here we're thinking of it as like, let the statistics work first and then let the domain knowledge come afterward, which is just like a different order of operations. So we go back to that example from the Calm app and just sort of apply this framework. So let's say like about 10% of users complete a first session on Calm, and about 99% of them don't sign up for reminders. So the event that we're trying to emit is sign up for a reminder event. And 1% of people do. And then 60% of people under that distribution, the probability of, in the third row here, we implemented a nudge that shocked people into being more likely to, that the instrument was applied. So we have a like counterfactual distribution of probability of D given X. Then we have this conditional expectation, which we estimated, which is that the people who didn't sign up for reminders would have 5 sessions in the next 28 days, and the people who did sign up will have 15. So we can now compute these interventional distributions for the conditional expectation and kind of figure out what the effect of this hypothetical intervention would be, and then density weight it to get like the total size of the opportunity. Yes.
So your outcome is retention?
Yeah, I just made this. This is a totally made up example, but it's sessions over the next 28 days is the Y variable.
The outcome is like whether or not sessions will continue over the next 28 days.
Right. Yes. Yeah. Yeah. Sorry, that wasn't clear. All right. So this is just an example of like how this would play out in practice, and like I guess we could if we had these what does this analysis require? It requires these distributions to be estimated. It requires the analyst to have an idea of the counterfactual distribution that they can create the new P of D given X, which is like if I put up a big screen on the app that said you must sign up for reminders and like made it really hard to cancel out or something like that. And they have an imagination for that and they can type in these numbers, and then the rest of the analysis just kind of like proceeds and they're able to estimate the size of the opportunity. So that's sort of like the input for the user is like how strong of an intervention can I generate? Okay, so the statistical problems that have come up in the course of that are this distribution over sequence prefixes, and then this conditional distribution of the outcome given the prefix, which can be used to do these interventional analyses, which are confounded, and we'll talk about that. So the confounding comes from just using the wrong adjustment set, plus having residual confounding, like that there's an unobserved confounder that we haven't adjusted for. So there's 2 sources of bias, just like conceptually, that aren't even statistical in nature, but just like because we're not conditioning on the right set of things. And then there's this bias variance trade-off, turns out to be really important here, which is like, how do you take a sequence and condition on it? Which is like, it sounds like a silly thing, but it turns out to be like a really important problem here. Is like, if you're doing you're doing dimensionality reduction, you're taking like an entire history for a user and trying to compress it into a representation that can be used in an efficient statistical estimator. And the properties of that will matter a lot in terms of the bias variance trade-off for both of these estimation tasks. And if you get them wrong, then your work is too noisy to learn things. And if you over regularize and use a really like kind of like high bias, low variance version of that estimator, then you end up not being able to surface any insights. So there's an important knob to be tuned here about just sort of like how flexible you're willing to be about these models that we're talking about. Okay, so we'll go back to this just to talk about the confounding side. I don't want to spend too much time on this because I think it's just sort of like anybody who works in causal inference will know that this is a confounded like DAG, and that like we have a little bit of information because it's sequential. So we're willing to say like Y can't cause D is like a thing that we know, and we know that D can't cause X. So there's a couple arrows that like have to go in a certain direction, but like generally there's this unobserved confounder and we can't say much about it. And what I'm claiming is we're just going to adjust for X and just not worry about it and just like live with the result of that. And the question is like, what are the consequences of that? And I think number one, obviously there's the, you're getting additional precision in predicting Y. So that's the bottom arrow here. Number two, it's the arrow, it's blocking the backdoor path through U and reducing the bias from thinking about D as an intervention, but also X is an instrument for D. So including it in the adjustment set is creating a different kind of bias as a result. So just to kind of summarize, we're over adjusting for the history. It's helping with confounding, but it's hurting with attenuating the effect of that D because the effect of D is already accounted for from things in the past that are instruments. In general, that creates an attenuation bias. And like for most plausible scenarios, you can think of that thing as an instrument, and you're conditioning on an instrument, it's going to make the effect of D look weaker. And I think that the main way I would interpret this is that we're doing an attribution analysis here. We're not saying D is like if we think about the credit for the user signing up or having a high retention, it's how do we partial credit between the experiment where we nudge people to do it versus actually signing up. And it's not actually clear which of those two things should get credit for it. Because the instrument does in fact cause it. So if we knew that the person was exposed to the experiment, that would be a valuable thing to know and to assign credit to. So we can view this as an attribution model where we prefer to give attribution to things that happen earlier in the sequence, essentially. And I think that I haven't really totally reckoned with the consequences of this, but for now, I think this is quite a reasonable thing to do. You can think about other attribution models, by the way, where you like could hypothetically remove events from the adjustment set and redo the analysis many times and try to do some kind of like Shapley value or something like that. But I think for now, this is a totally reasonable thing to do. And for most analysts, they'd want to know the earliest point at which information about something changing is revealed. Does that all make sense? This is the most casual I'll be about causality in my whole life, but go ahead.
So D has been binary so far.
Right.
Do you assume it's like the presence of one type of event or not? Is that what D is?
No, it's we'll talk more about it, but it's just like it is from a finite set of events, but it's not.
Okay.
But it's not necessarily binary. Yeah.
And you specify beforehand like which set of events D.
Right. There's a vocabulary of events. Yeah.
Okay.
You just think of them as tokens.
Right.
That's the most convenient way to do it.
Okay.
It's true that events have additional data about them, and we'll talk a bit about that. But thinking of them as tokens is very convenient for all the kind of like analytical work that we're going to do. And thinking of them as binary makes the trees really easy to visualize. So that's nice. It does make by the way, like the consequence of that is that the counterfactual is a little more difficult to define when it's not binary. So it's like D was set from a vocabulary. Which of the other things was the counterfactual? And I don't have a slide on this, but roughly what I would say is that the counterfactual is what happened before D was revealed, which is a little different way of defining it. But I wish I had that slide in here. Actually, I can dig it up. Okay, just to show like what has happened. I ran some simulations to show what happens when you do this kind of adjustment process. So the question here is what happens if I adjust for X versus not? So that's the left-hand side versus the right-hand side. Signal 0, 1, and 2. Signal is roughly how much information about the confounder is revealed by the history that I've observed for the user. So we should expect this to be stronger signal in cases where we have a longer history for a user. We've observed them for more time. We should expect it to be stronger when they do things that are more meaningfully predictive of what will happen to them in the future. And so it's just sort of like something that we don't know. We don't know how much confounding we're able to extract from the history of the user, but we can think about with more, the bias problem goes away. With less, it will be worse. And so like we should prefer to use techniques like this on longer histories, data sets where we have longer histories of events. And this method would probably work more poorly on cases where we have a shorter history and have estimated U estimated U via X in a worse way. And so adjustment tends to work well in most cases and be helpful. We're trying to get those lines to be alongside the dashed line. And you can also see some of the attenuation thing here going on where the slope of those lines tends to be lower than the slope of the other lines. So this is just to kind of confirm that like this is a reasonable thing to do, and you can vary the parameters of the simulation and try to say like, when would I be really wrong by like over adjusting in this way? And I think like it's just a kind of way to throw away the need for domain knowledge in choosing your adjustment set and feel like it's okay. Okay, so we're going to get to the statistical problems now that we set aside the causal inference. We're going to, with credulity, believe me about that this is fine. We need a representation of the user history. And I think the three main approaches that a kind of standard product analyst would use, probably the most common one would be feature engineering, to like just count specific things and to build a set of features that you want to adjust for. This is quite an annoying task. It's hard to get right. It destroys a lot of information. A way to do it with like a little bit less, this goes all the way back to like language models before LLMs, and like what were people just doing with language models to build predictors. And n-grams are very common. Back when I was doing my PhD, which wasn't that long ago, people would use n-gram models a lot. That's another idea about turning sets of events into a feature vector of fixed length. What we do a lot of Motif are prefix trees, and I'll talk about why. But it's a convenient representation for shorter sequences, which pushes the problem into sequence shortening as a regularization task. And clearly the bias variance trade-off here is that we need to tune this representation to be like predictive of Y, predictive of the treatment, and so like if we get it wrong, then we're going to have either too noisy, too high variance estimates, or too biased estimates. The thing that we work with a lot at Motif, because it's easy to visualize and kind of easy for people to understand, are prefix trees. So if you think about like a user flowing through a product, they're flowing through a tree, and so there's a set of paths or forks that they can make. And so the tree is a nice data structure for capturing that. And basically what we're doing is for every sequence, going through the tree and assigning a count to how many times that node was visited by that sequence. And so at the end, we have a tree that has a set of counts in every node for like how many sequences went through that node. So these trees, you can think about like the math of how many nodes do you have in a tree, which is effectively how many parameters. This is a distribution that we're fitting, right? It's an estimator for a distribution. How many parameters are in the tree depends on the vocabulary size or the branching factor, and then the depth of the tree. And so, but by controlling these two things, you're able to control the size of your representation. So it's a way of tuning how much how flexible you're willing to fit the distribution of sequences. Yep.
This reminds me a lot of epsilon machines. Are you aware of those?
No, I never heard of that before. Yeah, I would love to hear more about it. A lot of these ideas are like, if they sound like they're being invented from first principles, it's because they are. I don't have time to like read like 100 papers about how to do these things anymore in my new job. So like, if there's a way that I'm doing this that sounds stupid, I'm very open to hearing about it. One of the interesting things about the tree model is that the analysts can tune the flexibility of this representation by doing things that look like editing the sequences. So removing events, truncating the sequences at a certain point, splitting them into subsequences where it represents user behavior within a certain time period. So the act of making this representation compact basically boils down to operations which people can understand and iterate on, which is nice. So rather than having to tune the hyperparameters of the tree and say like, I need the tree to be this size and this many nodes, they just shorten the sequences until the tree looks the way that they want, and then they have the distribution. Then the other nice thing about prefix trees is that they have really nice visualizations available for them. This is a visualization not invented by, but first applied to user sequences by Carrie Rodden, who's a UX researcher at Google. So this is like 10 years ago now, but she had this insight that, hey, user sequences could be really nicely visualized by the sunburst visualization. This is the first visualization that we built at Motif for user sequences, and it's still a very useful one. And it's really nice because you can browse this visualization. So if you click on one of these segments of the ring, you can make it the center of the ring and then can effectively condition on a prefix and then scale out from there. And it's like an exact representation of the tree. So it's like it's capturing all the properties of the tree that you'd want to be able to capture. But note that the visualization and the tree both sort of share this property of that they're showing you their dimensionality. This visualization gets bad when it's high dimensional. When you have too many nodes in the tree, it's hard to read it. If you have a small number of nodes in the tree, it's easy to read it. And so it's almost exactly characterizing how flexible that you fit the data, which is nice. And we at Motif, we happened to have built the sunburst visualization first, but we started doing this kind of left to right version of it. It's just a change of the coordinate system, but it's really nice for longer sequences. You can kind of visualize them for longer, and for comparisons between two distributions of sequences, it's a nice visualization. So just sort of something that I don't think that we invented this, but it's just like I can tell you that it works really well, and it's like a nice visualization. And so some of the stuff I'll show you later does this left to right version of the sunburst, where it captures the same notion of time that when people look at a time series plot, it's like left to right is the passage of time. So that's a nice feature of it. The other thing that's nice about this is, oh, I must have missed it on the slide, is that the Y scale is exactly probability. So density, it's a density estimator. So when I think about how common is this thing, I just have to look at the height of the rectangle, and that will tell me how common it is. And if I click on one of those rectangles and condition on it, then I get a conditional density estimator. So it's a really nice depiction of the density of the event sequences. And I mentioned these simplification steps and how important they are for that. And I just want to say we build this into the interface because it's a thing that if you don't do it, that the sequences will be too long and the visualization will look bad, and you have this like high variance estimator rather than the kind of one that you want. So one of the most important ones is splitting sequences into pieces. So acknowledging that because the distribution is so high dimensional that you need to look at shorter periods of sequences in order to visualize them. So you either have to remove the vocabulary, remove a lot of events, and look at longer sequences. Or if you're looking at shorter sequences, you can look at more events. And so there's this kind of trade-off of like how far ahead into the sequence can you visualize, and how many events can you visualize at the same time? And so you have to let the user kind of tune that knob. And this distribution on the right is just showing that there are natural clusters of like time between events that you can exploit here to say like, okay, like this is sessionization is what we call it, but saying like, you know, the user is inactive for a certain state, they're probably then starting a new set of behaviors. It's very valuable for us because it shortens the sequences. And I want to throw in, since it's an AI talk, we did try to do LLM-based summarization of sequences, and I do think this is very fruitful, and we weren't able to spend enough time on it to get like great results. But it makes perfect sense to me to ask a machine to shorten an event sequence into more meaningful, shorter sequence, and I think that that's likely to work well. We weren't able to get it working well quickly enough to continue to pursue it, but like if I had a lot of time, I'd probably spend more time on this. One of the really interesting things here is like tuning the size of the compression that you're doing here, like giving the LLM the kinds of instructions that say like, I need a sequence of this length or this length or this length, and I'm willing to, is another thing that would be difficult in this context. But I know that there's lots of work on text summarization that could be kind of leveraged here. And GPT-4 can read event log data very, very well. So it's not like, it's almost like if you asked a human to parse through a data set manually for every single user and say like, well, what happened to this user? It can do that. It's just like hard to control it. Okay, so I'm going to talk about some of the estimands that I talked about earlier. The probability distribution over sequences is very neatly described by, so like we have this data set of sequences on the left, we construct this tree, we append it with the counts, and then we can build the tree visualization that I showed you already. So this is a really nice sort of like 3 ways of looking at the exact same data set. It's not lossy compression, it's the exact same data just displayed 3 different ways. And then I have the annotation for showing it that, yeah, the height of the rectangles is the density. Okay, so what is the expected value of the outcome given the prefix? And so let's say we had a count of how many success cases and failure cases. Every sequence is associated with like some success or failure criteria. Like the user was retained and came back in 28 days or not after observing the sequence. And we add that up, and now we have 2 numbers associated with every node. And then the visualization now is colored by that rate. And so it's kind of showing you like things that are productive, things that seem to be helpful for users, and things that seem to like hurt their level of conversion. So if they go from A to D, that's kind of like a bad transition. If they start with B, that's better than starting with A, are all things that can be readily viewed here. But if we go back to the estimand that I was most interested in at the beginning, it's the difference, the first differences of that visualization are showing sort of like the incremental outcome that you would observe given the transition occurring. So this is like a direct visualization of the thing that we started at the very beginning, which is just like, okay, well, what happens after A occurs relative to where we were before A occurred? So we can think about like the counterfactuals. We normally think about counterfactuals. We think about vertical comparisons across the tree. So A versus B. And what this is visualizing is different. It's the transition to A. So it's a step. It's like it's an Bayesian update of where we are after having observed this thing. But it's actually a little bit more convenient to look at it this way because you don't have to define a baseline condition or whatever. Effectively, the baseline is the weighted average of all the steps that could have been taken. And so it gives you some kind of effectively like a weighting for the average treatment effect, but it's very, very similar and correlated with it. And now you can see like there are these hot spots and cold spots. And so it's a really nice visual. It's like a heat map for interestingness. And remember I said before, the height of the rectangle is the density. So we think about opportunity size for an analyst. This is exactly doing what we want, which is that the color is strongest when the magnitude of the effect or the quote unquote effect is large, and the height of the rectangle is large when it's a common situation. And so we're using all the visual dimensions that we need here to show exactly what we would like to be showing, which is sort of like where are there interventional opportunities in the data set. I'm going to talk about, before we get into, I'm going to talk about doing this in a fancier way, but I just want to mention some interesting kind of other ideas here, which are that like this is a joint distribution between an outcome and the context. You can invert it and do like, analyze an A/B test this way and say like, well, how do these sequences differ in the A condition and the B condition? And it's a very, very similar calculation to do here. And another idea that we've been pursuing that I don't have a good sense of how to do exactly yet is to sparsify this tree, to like build the tree and then remove nodes that aren't informative. Very, very similar to a decision tree where you sort of like, if there's no information gain, you can omit it. So it's another compression that you can do if you have a label. But you can't compress the tree otherwise, but if you think it's like, this is not an interesting transition, then you can sparsify it and maybe the visualization could get better. All right, so I talked about the prefix tree model. Let me do another time. Okay. I think like we try to straddle some middle ground here where there's like an interpretable set of states for users to be in. The parameterization is small enough that we can fit the distribution pretty well. And it's sort of like, so it meets some requirements, but there's this idea that like maybe we over regularized and like we have too low of dimensionality to really surface the interestingness in the data. We did have to make a lot of assumptions, right? Like we didn't include other dimensions that are available on top of events. So sometimes events have other properties that we want to capture. We didn't capture time between events in any way. So there's a lot of information that was still discarded in order to create that representation. So one of the other parallel projects we've been working on is like, can we just use a deep learning model to characterize the event sequences? And so I'll talk about that. And this is much earlier work that I don't think we've been super successful at yet, but I think it's a natural fit for some of the transformer stuff that's coming out. So it's sort of like, this is a slide. Sometimes I show investors because we want them to give us more money, and we want them to like see that we're doing AI stuff. And there's this natural analogy between like language models and sequence models. And one of the interesting differences is that we don't care about generating sequences. Like that would be a really nonsense thing to do. We already have the data. We don't want to like generate suffixes to data. What we want to do is like predict some outcome, and it's not usually the next event. What we want is like something kind of in the longer run. So there's just like a little bit of different like fine tuning step on that model that needs to be done, but otherwise very, very similar kind of setup. And so like we can leverage a lot of the same technology that people are doing for generative AI. Probably the only trick you need to invent to do this is to turn an event. This is what an event looks like in Motif, by the way, is that like an event has a name, it has other properties about it, it has the actor, which is the person who triggered the event, has a timestamp, and there's just lots of other information in there. So it's a pretty rich, it on its own is a high dimensional thing. So what we do in Motif is in our demos right now is we've been just like concatenating these events. So you can think about like, as I take an event, I could break it into sub events, and then just, you have to give them some ordering and time, but you just make it arbitrary. And now you can kind of like scroll through an event sequence and find, you know, like as of having observed this event requires like moving more than one token. It's like a mapping between, it's like the mapping between words and tokens. We have to do something similar here where there's multiple tokens per event. And then to just kind of draw the analogy and make it complete is what's going on in a transformer, right? It's like there's a set of events that were current that are being observed. We have this context window. We take the events and convert them into embeddings. We use that context window and an attention mechanism to create a representation of the state that we're in at this exact time. And then we use that state to predict the next event probability and compute a loss function. And we did this at Motif, and here's what it looks like. This is one of our data. I think this is our, I'm trying to think about, this is our data. This might be customer data. It might be our data set. I forget which one it is. But we do this, and then we can take that embedding, and then it's the last layer before we emit the prediction of the next event, is a representation of like the state that the user's in. And it's tuned to predict the next event. So it's really kind of capturing like in this lower dimensional space, people are likely to do the next thing. The next thing is likelier to occur, and users have paths through this latent space. And this line here is an example of that. And we can like map it into clusters and show users kind of moving between clusters as the representation of user behavior. So this is a really nice like dimensionality reduction technique. I think we've struggled a little bit with interpretability of these clusters, as I think you always do when you try to project a latent space. But it's an interesting idea, and I think clearly the models are capable of doing this very well, and they don't take as long to fit as a normal LLM because like the data is a lot smaller. You don't need to learn about all the world. The properties of the world, like the causal system that the model is trying to reason about is much more simple and compact than like a whole language. And so the trick to getting this to do stuff that we need is to take that outcome and redefine it. Instead of predicting the next event, what I need to do is predict properties of the suffix of the sequence. So like what happens next. And so we think of this as like a user specified thing. It's not to be learned. It's something that we need to specify. What is interesting about the rest of the sequence that you'd like to learn? And then we have the second loss that we can add to the loss function. And we're using the next event probability as a way to kind of like give it a high signal thing that it can optimize for and create a good representation. Then we can tune that representation to predict these longer term outcomes and try to understand if the change in the event is likely to lead into different longer term outcomes. There's a little play on transformers, which is that like most transformers are very myopic. We're trying to just predict what happens next, but we need to predict a longer time horizon. It's a slightly different learning problem. But it's noisier, right? So it's like you don't want to train your representation on this long-term future because it's a much harder thing to predict, and the model will take a longer time to learn it. So then you would need more data. And then some examples of like other systems. I really like sports analytics. So an example of like this approach being applied in other settings to create like transition value. When you have a model like this is just like wind probability models in sports are using a complicated representation of the state of the system, like many variables. And they can use that to construct a probability that a team is winning the game or will eventually go on to win the game, which is a longer term outcome. And then you can use this to do attribution, right? So you can say like at each time step, I can map this to a real number, which is the probability of winning the game. And then I can compute the first differences, which is exactly what we were visualizing before. And then we can, so on any individual sequence, we can produce a time series chart of like what that sequence, how that sequence evolved over time, projected into one dimension, which is like the reward dimension, and then do this attribution thing. So it's like, down to the event level attribution on the full data set, which I think is kind of cool. And so I just have a little example and then I'll wrap up. This is real data from one of our customers, and just sort of like, if you take the raw events, this is very, very similar to the tree visualization I was showing you, right? It's just unordered. So I'm plotting individual events instead of clusters of events. So it hasn't been put into a tree yet. It's just laid out left to right. But if you sort it, you get clusters. So it's just sort of like, and if you have sequences and you have one dimension to represent the variation in the sequences, then sorting them is a clustering technique. And so you can just sort them and you get this. This is a density estimator, and it's actually exactly the same as the tree visualization. If you do the sorting order the same as this order of the tree nodes. So it's kind of neat that works out. And we still get the nice property of vertical space proportional to probability. And then we can label the outcomes in that diagram. So say like, where did the good thing or the bad thing happen in the sequence? And then we can apply the model to predict those outcomes and compute that expected value, just like we talked about before, except for now it's at the individual event level, like at every individual sequence. One of the things that we found quite useful is on many of these sequences, there's no variation in the expected value, right? Like many sequences are uninteresting sequences. So call this like opportunity filtering, but you can, like, if you want somebody to surface interesting variation, you want to just remove things that don't vary. That's a very valuable thing to do. So this just takes these paths and finds the ones that have variability in them, and then we can zoom into those. It does make the probability distribution quite a bit smaller. It's like a kind of a conditioning that we're doing. And then we can do that first differencing idea that we did in the tree structure, but on the individual level data, and try to spot like, okay, where is there interest? Where did some event occur that really meaningfully changed the outcome according to the model, the probability of the outcome according to the model? And this is, I think, like maybe not so different than how humans conduct causal inference, is like in their heads, is like if you burn your hand on the stove, it's an n equals 1, it's a single event, but you know now that stoves cause hands to burn. And in this high dimensional space with events that are not really like, you don't have a perceptual system designed for this, what we need to do is sort of create heat in a different way, create that sensory experience. And this is just an idea about how to do this. And then to go back and then interpret roughly what was happening, what was the setup, what was the context, what was the action? Is this something that's intervenable? Do I have control over it? And all those things happen later, but like this is a good way to, and it's very related to the tree diagram that we showed before. It's just sort of individual level version of it. All right, so I'll wrap up there. I think that I've worked on this problem for a long time now. This is my current state of thinking on it. I think it will continue to evolve, but I'm quite pleased that like the links between everything that have come up, it just sort of seems like that there's a lot of opportunity here to do a better job. The visualizations and the distributions and the objects seem to really go together really well in practice. And then now there's this kind of like user interface problem that we're working on. And I'm not going to do like a Motif demo in the middle of the talk, but you should check it out because I think we built a nice UI for working with sequences. And if you work with data like this, this is kind of, it's important to have the affordances to alter the data and manipulate it to use these visualizations properly. And there's these two main approaches that we're sort of like honing in on. One is this human-defined, changing the data in a way that makes tree visualizations work well, or building a latent space and trying to figure out how to like map the latent space into visualizations, which is like a kind of longer-term project that we're working on. And I think that the encouraging part for me is how much domain knowledge still goes into this problem, which is like, I don't really like working on problems where there's just like, there's a there's a loss function and you just minimize it and it's just all like modeling and optimization. This is something where humans still have a really important role. Like where did the Y variable come from? How was it defined? Which helps guide the dimensionality reduction. Which events are important to include and not include? How do I know what a sequence really means? What is the start of a sequence? All these distributions like sort of require you to define what is the start of something, what's the start of the process. And so there's all these interesting roles for human domain knowledge in this process. And so it kind of almost requires you to build an interactive tool to be able to do this kind of this technique. Just like you could build a virtual eye, but if you couldn't figure out how to aim it and like filter out the stuff that's uninteresting, then the eye wouldn't work very well. And finally, like this causality stuff is a really important thing where like it's an imaginative act that humans have where they can picture an interventional distribution and in their heads and say like, is that even possible to make that event happen more often? So there's this active imagination that I think humans still have the capability of doing here, and it helps a lot with this kind of analysis as like an additional filter at the last layer. Okay, I'll stop there and take any questions that you guys have. Yes.
One question I have is, it appears that when you're making these predictions, or trying to make some sort of causal inference, saying this event caused another sequence, it's a question that comes to mind is how do you control for confounders that it sounds like you're not really accounting for them, which is fine if you just, they're unobservable confounders, but could you run into problems that doing that?
Yeah, I think that the problems have like a really kind of, I agree with you. We're not doing a very rigorous job of this, and it relies a lot on like assuming that you have a lot of information in the history of the user that can reduce the confounding, but maybe, plausibly never eliminate it. But the idea is, what's the failure mode of that? What's the cost of getting it wrong? And the loss function for exploratory work is very different than the loss function for like confirmatory work. So I'm trying to say, like, does smoking cause cancer? I wouldn't do this because actually it's funny, in smoking, they actually had to do a lot of work like this. But for important things, I think you still want to run experiments and test them. But I think that like for the failure mode here is that you usually learn something mechanical about the system. Like, oh, this thing made the probability go up. It's like, it clearly reveals information about the user rather than it is interventional. And so you can kind of like tag these hypotheses that you generate as like, oh, this is just revealing information about the confounder. And so it's not that interventional.
I see. And if I understand you correctly, it is hypothesis generation, which presumably the customer could then test with like A/B testing, right?
Right. Yeah, that's the idea.
So they have much more control than say many social scientists do.
Yeah, I mean, in most of these settings that they're actively looking for things to change. It's like the job wouldn't even exist if they couldn't make changes to the system. So the goal is to surface like things that are more likely to succeed upon A/B testing them. Yes.
So going back to like your original, like the very generic kind of diagram you show with the experimental manipulation happening on the scheduling. I'm just curious, what are your thoughts like when you're dealing with this kind of data on the timing of like the manipulation or the timing of these experiments? So in the example, intervening with someone within their first 28 days, day 3 versus day 8, how do you all think about those kind of questions?
Right. Yeah.
Operating in this space.
Yeah, so typically, I mean, I can tell you about how these tests typically are run, which is that they're not conditional on anything about the user. Usually it's like an unconditional randomization. So they'll be like, we will produce this nudge, but I guess it could be targeted at new users. So maybe that nudge would be like gated to people who are doing the sign up on the app, but it could just be something that like the next time you open the Calm app, it decides to like try to encourage you to do that. So it would depend on the design of the test. And then the timing of the outcome is something that you can study, right? So you can condition on what do you know about the user at the time that they were assigned treatment, and do kind of heterogeneous treatment effects on top of that. And if you're interested in the timing of the outcome, you could study sort of like time until, or like a richer definition of retention. How long did it take for that effect to take place? How long did it persist? So there are all these ways to complexify that design of that experiment and analysis to get at those kinds of dynamics questions.
Okay.
Yeah. Yes.
I have a question in terms of the transformer part that you talked about.
Mhm.
With neural training, do you have a set of defined labels where what users are going to do in the next step or in long term?
Okay, so what we do is we take the event sequence, the data, turn it into tokens. So it's a token stream. And so just use like an encoder, token encoder for that. And then the tokens are given vector representation, but then the labels are just, it's the one step ahead objective.
So the next token.
Next token prediction. And then what we've been playing with is adding a second loss to it. And so the second loss is something we can compute by streaming backward through the sequence and saying how many of accounts of this event will happen in the next 15 minutes or something like that is a thing that's known by only looking into the future, and you can assign a position in the event stream. So we get the second set of labels that come from the future, like further into the future. And we can use a loss function on those as well. What we've been playing with is like a histogram of events in the future. So predicting not only the next event, and then you have to destroy the timing information for the future and say like counts of events at various time horizons for the next, day or something like that. And we use that as a loss. Yeah. Yes.
Can you kind of framework we described with events can be used to kind of model natural experiments, and does it suggest actually like computational methods for discovering those and data?
Yeah, that's a good question. Like I talked about panel data at one point, and I guess most people would use sort of like a difference in differences sort of study, or just a first differences. And I do think there's a deep relationship there, but I haven't quite worked it all out yet. But I do think you could use this method if you tagged events as like user was exposed to natural experiment. I think you could use methodology like this to understand the effects. But I think that in general, this isn't a rigorous estimation methodology, like for like estimating the causal effect of something. There's not like, there's no inference here. It's just estimating an expected value difference. So yeah, I guess there's some relationship, but this is way less rigorous and more geared toward perception and visualization.
Just one last question. The very last slide, you said try it out. Is your visualization available? Or?
Yeah, so there's this is a product, but we have a free version, and it runs in the browser. So you open data. The data have to have 3 columns, timestamp, event name, and an actor ID of some kind. And then all these visualizations just like work. They exploit that structure to do that. And then the only thing that's not provided is the deep learning stuff is like, well, we need to move that data into our data center and do it there. But other than that, you can use all these visualizations. So anybody, if you want to try it, just there's a sign up, and then I'll just enable access for you. And you're happy. I'd be happy to have feedback from folks. I think it's I find it very useful for just like if you're opening a data set for the first time that looks like this, it's like a very good way to just do EDA on it and understand what's in the data.
We're at time, so thank our speaker again.